Yeah, so we're in Hilo, Hawaii. I'm Brian, for people that don't know me. And we have Denise here and Jenny that are observing and operating respectively. Those are our nouns, I guess, for the roles that are that Denise and Jenny have tonight. And so we are actually acquiring on a this is a standard, right?
Yes.
Yeah, so this is a telluric standard for a near infrared spectroscopic observation. And
Starting science.
so we just got acquired. The image that you're seeing now is the through slit image, and Denise is checking the data. I'll go back through that in a second. Did you see mind if I do something on there?
One sec.
Yep. So we just took what was about a half an hour long observation, 45-minute long observation, science observation. We have to do a telluric standard in between, and then we're going to go back to another science observation of the same program. And this is looking at freely floating planetary bodies with our Gemini Near InfraRed Spectrograph, and they're using cross dispersion. So cross dispersed spectroscopy. And you'll see what that looks like in a second, but this is our acquisition image here. So this was the target standard star. And then we closed a slit on it. And now we just took our first cross dispersed spectrum. Let's see if we get this. Okay. So this is what a cross dispersed spectrum looks like. This is the trace of the standard star. You can see night skylines here in the background, although these are very short observations, so there's not a lot of sky in them. These are the different orders that we're tracing. So this is the K band. This is about 2.1 microns, all the way to X band, which is roughly about 1 micron-ish. And I'll let Denise take over. So this is the fast part. We're going to be doing a bunch of movement here, and then we can pause for questions.
Okay, Jenny, can we slew you to 45?
Okay, so we just finished with our standard observation, and we're slewing now to our second target for this program. This will actually be likely our last science target for the night, I think. Is that right, Denise?
Yes. Well, Maroon X is after this.
Are we going to do Burn X? We're going to try?
Maybe.
So this, what are we at? 4:41 right now?
Yeah.
So, oh,
We're ahead of schedule according to this, so there might be time.
What's how long is that?
This one?
The LP202 program?
10
minutes. Oh, we can maybe get that. Okay. So we're just checking our queue right now. So we're checking which observations we can potentially take to end up the night. So for those who you don't know, the Gemini North telescope is on a queue system. So Ting, have you guys, what other telescopes have you guys seen? Keck?
They have CD cam. Well, CAC was weathered out. It was the same week that last time.
Yeah, okay, yeah.
So they see dark energy camera on Blanco through the remote
Okay.
imager. Yeah. So they never
Okay.
see spectroscopy. So this is very good.
All right, thanks.
How
long? 200.
So was that run under Q or that was run under, because they do classical nights and Q nights, right?
They do classic. So my postdoc is night, and then he took some student to do the remote observing.
Okay.
Yeah.
Okay. So yeah, so we operate under a Q system. We do have like it's very rare, but we do have classical nights. That hasn't happened. I don't know,
Starting acquisition.
since I've been working here, but I've been working here during after the pandemic started. So yeah, the queue system works where everybody submits proposals. They're graded. We have different priority bands. So band 1, band 2, band 3, band 4. We then rank the observations based on their scientific priority. And then we use a variety of factors to determine which observations we're going to take on a given night. And so right now we're in band 1. So this is the best that you can get, highest priority. And we're going to try to get, so right now we're taking the cross dispersed near infrared spectroscopy. And if we can fit it in right after this observation, we're going to move to high precision radial velocity observation with Maroon X in band 2. And that'll just be a 10-minute observation. So we'll have about half an hour here, if all goes well, and then about 10 minutes with Maroon X, and then we're going to end the evening actually doing a focus run. So this should be perfect for you, Ting. This is like we're actually going to check the focus of one of our peripheral wavefront sensors and see if we can. It actually hasn't been done in maybe 6 or 7 years. This is our secondary peripheral wavefront sensor. And so we'll run through like a focus loop, and so we'll get into the details of how we do things here at Gemini. So what I'm showing right now is our what's called our telescope status display. So that's the screen here. What we're seeing is here's a depiction of the Gemini Dome, Gemini North Dome. Here's where we're pointed. Here's the moon, actually. So we're right next to the moon, which is mostly fine since we're in the near infrared.
Paused.
And so this is where our telescope shutter is. So the big opening in the front. This is where we're pointing. And these are various elements of the telescope down here. So this is the primary wavefront sensor 1 here, which we're going to tune later. We're going to
Sending offsets.
This is our secondary peripheral wavefront sensor. So this is the one we're currently using. It's our preferred wavefront sensor.
Great, thanks.
This is our adaptive optics wavefront sensor here. So this is for a unit called ALTAIR, which is our adaptive optics system. And this is for the on-instrument wavefront sensor, which is used for GMOS, which is an optical instrument, which we're not going to actually be observing with tonight since we're near full moon. One of the neat things about Gemini is that unlike a lot of other telescopes, we can switch between instruments really, really quickly. So we have a deployable tertiary down here. This is called our science fold. This is what we lovingly call it. So we have light coming in, hitting our primary mirror, our monolithic primary. So not like segmented, but monolithic. Light is then directed to the secondary, which is then directed down to our what's called our cast cage. And this contains all of our instruments. And the deployable tertiary redirects the light to whichever instrument we're using at the time. And so in this case, we're using GNIRS, and so it's sending the light to GNIRS, and then Denise here is controlling the GNIRS instrument, configuring the different optical elements so that we get exactly what we want, in this case, cross dispersed spectroscopy. So these numbers up here are all about where the telescope is pointing, what the rotation is of our cast gauge, our instrument gauge, various numbers associated with the instrument. So where the instrument is, basically where the light comes in to the instrument. If we send the light there, various offsets that we make onto the sky, that's what this P and Q is. And then our seeing value. So currently we're measuring seeing about every 5 seconds or so, 10 seconds, with our secondary peripheral wavefront sensor. And so you can see the seeing in the V band is about 0.5 arc seconds, which is quite good. It doesn't measure it all that well, so we have to take that with a grain of salt. But it gives us a rough idea of what conditions we have.
It doesn't look like you're tracing this light.
1 second.
Okay. So while we are waiting, I just want to tell people that you may see that in the room, there's people talking in the background, which I believe, maybe Brian can say more later, which I believe is there's a telescope operator controls the telescope where the telescope flew to.
Ignore offset.
And then there's astronomer there doing the observing, decide which target to go, and then control the instrument. So there's these kind of conversations between them.
Okay,
So take the second one, and then you'll do a sky subtraction.
Oh.
Yeah, so anytime you see the P or Q offsets, that means
In our case, the SOS will.
So I do, and then the first one's the sky?
first one, sky, yeah. Getting up to your microphone, like
I was just mentioning. Not just the instruments. Telescope.
yeah, you guys do everything. We're the lame ones that only do half of it. Let me switch over to the acquisition. So this is the slit that we're using, the process first slit in GNIRS, and Denise is hopefully gonna see something pop up in a second. Yes, perfect. Okay, so there, kind of. So it's good.
Oh, it glitches.
So that's our science target. The
Is this not why there is a black dot next to that bright one? I assume the bright one is the actual star, the target.
exactly, yeah. So this is the
Starting science.
freely floating planetary body, I guess, that they're targeting. I know nothing about these types of systems, but that's what they said in the proposal. So it's fairly faint. I guess what's the magnitude they say it is?
Target. 17 in H.
So 17 in H, Vega. So yeah, not super bright. And so we actually needed to take a sky beforehand. So we basically knotted along the slit, the major axis of the slit here. And this is the negative image. So this is an A minus B image. So we have our centered observation, our A location, and then a B location. And so when you subtract the two images, you have a positive and you have a negative.
So you also do not unshuffle during acquisition.
You do just nod. Yeah, so no electronic shuffling or anything like that. But yeah, we don't if the target is bright enough. But if it's in the fainter regime, then we do that because it's a lot easier to pick up. And we want to make sure that we're nice and centroided. These observations, so our what's called focal plane unit is a 1 arc second wide slit. So this is actually the widest possible slit that you can have for GNIRS. But if we had a narrower slit, it'd be really important to make sure that we're centered. And so that's where the additional precision of the centroiding process comes in from doing this knotting. Otherwise, you have a relatively faint source on top of a very bright sky, and it's hard to centroid that.
Yeah, I don't know what the best way, should the student just ask, or they post some in the chat, or they raise the hand?
Anything, there's enough, there's not very many people here, so we can make it nice and easy. Please, guys, if you feel so inclined, ask any questions. So I can just start like kind of cycling through our screens here. So actually, you can see in this camera view, I mean, we have a ton of computers. We have a ton of things going on in this room. Denise actually has 8 screens that she uses. Jenny has 8 screens that she uses. There's some overlap redundancy there, but there's a lot of information here, so I can just kind of start cycling through and then.
Before you move on, I just want to make sure people understand this image. I don't know, because it's their first time probably see spectroscopy. So this basically is the image of the slit. So as what Brian mentioned, this is infrared spectrograph. So we want to get the target, or this I think it's a star, get a target into the slit first. And then, so that's what we call acquisition image. And then now I believe they are doing the real science exposure to get that star to the grading, to the spectrograph, to the detector, to get a spectra. But before that, you want to make sure the star is inside the slit. So you want to take these kind of acquisition image. So you can see the image in this image that the star is very nicely in the center of the slit. So that's why they went to the science exposure. I want to make sure that's clear to people.
Yeah, thanks, Ting. That's exactly right. So yeah, we just got centered, and so it's much easier to center when you don't disperse the light. Once you start dispersing the light, things become a lot more complicated. So this is literally just an image, but it's an IR image. And so it's an image through a very, well, for GNIRS it's large, but a very narrow aperture. And we're just making sure that we're dead on centered, that we're getting all the photons that we possibly can get. And then we move over to, we shift everything over to our spectroscopic setup. And as you said, we start dispersing the light and everything. So let me. Okay, so this is what GNIRS looks like. And this may help. It helps me a lot to. I'm the instrument scientist of this instrument, of this behemoth, and I always have to go back to this diagram. So, you know, it's fairly complicated. It's a multifaceted instrument. It has imaging capabilities, a lot of different spectroscopy. We just commissioned 2 integral field units on it. So these are image slicers, basically spectroscopy of every portion of the sky that you look at. It's about 3 by 5 arc seconds is our largest one. And so general principle is that light comes in from the telescope. So that's what I showed earlier. Actually, I can back up. Okay, so this is our light bucket here. And so light comes in, all 8.1 meters times pi squared, area of the mirror minus where the secondary is, collects the light, then goes in secondary, then tertiary, then GNIRS, and then that's where this diagram starts. So then the light comes in from the telescope. If you saw earlier, there's this like weird keyhole shape. And so this is this component right here. So we have the science light going into the keyhole, and then it used to be that GNIRS had an on-instrument wavefront sensor, so that's where the rest of the light went. No longer exists. So that was where this was, and then we have either. Actually, it's probably easier going down here. So we have stuff coming in from the telescope, blah, 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 blah. And then it's a collimator. It potentially hits this acquisition mirror if we're acquiring. And if it hits the acquisition mirror, it does not interact with any of our dispersive units. So either our prism or our grating, this occults the beam light that comes in from the telescope, so this acquisition mirror. And so we just get white light, and that's what we're using for our acquisition. And then that light is sent in to one of our cameras, and then finally to our detector here. If we take the acquisition mirror out, which we do at the end of our acquisition process, then the light is allowed to interact with our dispersive units. So we have this prism here, and that prism can either be used as a cross dispersion, or there's a what's called a fold mirror with on this turret. So there's basically a table in here that can turn around. And so the fold mirror just basically reflects the light. So we say either we want the cross dispersed, meaning we get all the wavelengths of light that GNIRS is sensitive to, or we'd rather just have some portion of the light. And so then we just put the fold mirror in, and then we send the light over to one of our gratings. And so we have 3 different gratings on GNIRS. That's what this shows. And then once the light is dispersed by the grating or prism or both, then it's sent again to the camera and then again to the detector.
I'm not sure if anyone has questions. I'll just read out. Actually, Phil has a question earlier, but let's do this one first. What exactly does the grading change? Is it resolution?
Yes, so the grading changes the resolution, and it changes, so by changing the resolution, it changes the wavelengths that you can see. And so you basically have a finite amount of detector real estate. And so if you increase the resolution so that, you know, a certain number of pixels corresponds to a smaller number of angstroms or nanometers or microns, whatever your favorite unit is, then you have a smaller dispersion range, so smaller delta lambda that you're observing versus a lower resolution grading where you could get more, a larger dynamic range of wavelengths in a given observation. But this is where cross disperse is really amazing, because you basically, so with our 32 line per millimeter grading and our short camera cross disperse prism, you basically get, what is it, about anywhere between 3,000 and 5,000. And so maybe 5 angstrom resolution across all wavelengths that GNIRS is sensitive to. So all the way from 1 micron to about 2.5 microns. So that's very powerful.
And I also want to add the grading also has different grading that's sensitive to different wavelengths, right? So it's not only resolution and also the wavelength range, but also in principle, you can choose a particular wavelength range you want, and then pick the grading that has the peak efficiency or the what we call blazed angle at that particular wavelength to maximize your throughput.
I did check the first one. You can see the line.
see it, okay.
And I'm not sure people get the cross disperser idea. So you all probably learned the grading, the diffraction formula, d sine theta equal to m lambda. So you know basically that's the light dispersed, but the first order, the second order, basically, for example, in optical, in the first order, if that's like 400 nanometer, then in the second order, it will be 800 nanometer, it overlaps. So if you don't use a filter, you will have all these light at different wavelengths overlap in the integer, times of the wavelengths. And if you use a disperser, you will disperse those light that in perpendicular to the dispersion direction. So you will see multi-order. I think there was an image earlier. Maybe when this exposure read out, the student will. Are you guys currently taking a cross dispersion mode or taking
We are, yeah. So
you'll see that. So there was multi-orders of spectra instead of just one order. So in that way,
yeah.
you can cover, I believe for this instrument I saw, you can cover from 0.8 micron to 2.5 micron in one exposure, right? If you only have one order, you can never cover that because the in one order, 0.8 will overlap with 1.6 micron, just simple diffraction equation. But because of this cross disperser, it will break into multi-order. So that's how usually we do high resolution spectroscopy for measuring like stellar abundances or to do any high resolution stuff.
Yep, exactly. Yeah. So this isn't particularly high resolution. This one is about R3000 to 5000. But yeah, if you had like Michelle spectrograph, that would be a similar type of principle. I think there's multiple prisms involved. But you get, yeah, really high resolution. In fact, if we get a Maunakea observation in, that is a very, very high resolution spectrograph. I think it's centimeters per second kind of resolution. So that's, you know, get a ton of orders there. And I think there's multiple prisms involved in that, although I don't know that instrument. Well, that's a visiting instrument. So actually, I just got trained on observing with it maybe a couple months ago. So it's still, but yeah, so that's the basic idea. In fact, so for GNIRS, our gratings are all sensitive across a large wavelength range. Otherwise, cross disperse would be completely pointless. So so it doesn't matter too much the wavelength range that you, or sorry, the central wavelength basically that you choose. Which grading you choose is not highly dependent on that. But for like the GMOS, the optical spectrograph, and imager, choosing your grading based on your central wavelength, based on the blaze angle, is extremely important. If you, let's say you want a red observation and you choose a grading with a blue blaze angle, you're basically going to lose 5 or 6 out of every 7 or 8 photons. So it's not going to be good for your science.
And Brian, there was a question earlier that Phil asked if you can answer, because I think you guys mentioned before this current exposure, you guys was doing a standard star. So the question he had was, do you usually always take standards between every observations? Maybe also the add question for me is, do you usually do calibrations in between these every observation? Can you say a bit of that?
Yeah, those are great questions. It depends on the observation. So that's the first answer. With near infrared spectroscopy, that's kind of the most intense set of observations in terms of what we call overhead, so calibration stuff. And the reason is because the atmosphere changes on a fairly short time scale, and there is telluric absorption, which removes flux from your astronomical source. So you have your astronomical source, you have its intrinsic light, hits the atmosphere, it's absorbed to some level. There's a lot of these telluric bands in the atmosphere, and then you receive it at the telescope, and then you do all of your normal, flat fielding and all these kind of things. And so basically, you need a spectral flat for the atmosphere. That's how I think of like a telluric observation. So instead of sensitivity as a function of location on the detector, it's a sensitivity as a function of wavelength. And so what we do in the near infrared is we take these what we call telluric standards. So basically you have a star of a known type. Usually it's a like A or B star. So you can take synthetic spectrum of that star, or you can scale Vega or whatever you want to do. You take a known spectrum of a star of that type, you scale it to that magnitude, and then you compare the observation that you get with that template. And any changes, assuming you've matched everything well, it's the correct spectral type, so on and so forth, any changes from the flux that you expect on a relative level is due to these telluric absorption features. And so you take that quotient basically and you apply it to your science data under the assumption that the science data that you took had the same telluric absorption as the standard. And so a couple things for that is you want it, ideally, if you had like a multi-object spectrograph, you'd want to be taking a telluric observation at the same time as your science observation. That would be the ideal case, because you're getting at the same exact time, at the same exact location on the sky, feedback on what the atmosphere is doing. But we don't have a multi-object capability on this spectrograph. And so what we do is within an hour and a half of the observations that we take for your science, as soon as possible, as soon as your science is done, basically, or just before your science starts, we take a telluric standard and we try to match that as best as we can to the air mass of your science target. And so air mass is basically the amount of atmosphere that you're looking through. Matching it temporally is really important because the atmosphere changes dramatically on fairly short timescales in the near infrared. And so we're taking that standard, matched in air mass, matched in time, allows whoever's proposing and getting the observations to correct their data for this telluric absorption. Additionally, we take flats on sky, and we take basically internal flats, and we take arcs. And this is because of gravitational flexure. So we can't just take them, at any time, because the trace of the different orders. So, for example, in this plot here, the location of these different orders will change based on gravitational flexure. They will also change based off of different optical elements. So actually our prism inside of GNIRS is a little bit wobbly to like a few pixel kind of precision. And so supposing we go to some other random source and we take your observation and we're like, okay, good, we took your observation, your science is done, yay. Then in the daytime we're like, oh, we'll take care of the flats and the arcs during the day. Well, the flats are used primarily to trace the orders in the data reduction. And so if we take a flat during the day and we're off by 10 pixels because the prism has shifted, that's not good. It can be corrected in software, but it makes everything more painful. And so we prefer to just take the flats and the arcs immediately after the science. And so we have everything nice and calibrated. All the optical elements are exactly where they were when we took your science. So everything can be matched up perfectly. And so those are the kind of three calibrations that we take for the near infrared. Now for optical, we don't do that. So optical, we don't need it. The telluric bands are not as prevalent and not as prominent. And so for imaging, for example, we don't even care. The only thing that we need is one photometric standard per night if the imaging programs require it.
Can I ask a follow-up on these things, Brian? So you mentioned basically right now for GNIRS, you do flats for getting the tracing and also arcs to get the wavelength calibration. And then you also you do that at right after every exposure. And then for telluric standards, you said you do every 1.5 hour-ish.
Mm-hmm.
So all of those are things that do by default for this instrument, or it's something PI when they write their proposal, they need to specify and they need to submit this during the phase 2 to say, I need tellurics, I need to have calibrations right after exposure. Or that is just what you do by standard. It would be good to know for the group, how these kind of calibration work of the proposal.
Yeah, it's a great question. So we it's a kind of complicated answer, but basically we have we have what we call baseline standards. So as part of like a service of the observatory, let's say. Let's call it like that. So customer service. We provide a certain level of standard. And so that would be telluric standards in the near infrared. That would be our flats and arcs, this kind of stuff. Now you can go beyond that if you like. So if you would like to flux calibrate, you can actually use the tellurics. It's not that big of a deal. But supposing you want like really crazy precision on your fluxing, maybe you want to ask for a second standard that's a flux standard. That we don't provide. And so that you have to ask, it basically comes out of your science time. So you have to ask as part of your proposal, you say, I want this extra 10 minutes because I want to do blah, 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 high precision fluxing or something like that. And so then that would be charged as part of your normal program. So we have partners. So Gemini is operated by 6 partner countries. And we have partners that have a certain amount of time kind of collective for the country. And so standard time, the time we use to take telluric standards or any sort of calibration during the night comes out of the pool of time that's associated with that particular country. And then there's the principal investigator time, which is science or any additional calibrations that you'd like to take.
Okay, so for GNIRS right now, these arcs, flats, and the telluric standards are part of the routine thing you guys do, and you don't charge to PI.
Exactly. Yeah. So I could actually show maybe. Let's see. Okay, so this is yeah, you can see this. Okay, so this is our observing tool. And this is like super complicated, but this is how we all interact at the observatory, and all the partner countries and all the principal investigators, the proposing teams, everybody uses this tool. And this tool is also used at night to queue up our observations and configure all our instruments and everything like that. So this is our keystone at Gemini in terms of getting science programs ready and then observing them at night. And so this is just my personal workspace, just random things that I try out. And in this particular case, we have so time accounting is very important at Gemini because everybody wants to get their science in, and we only have a certain amount of time on sky. And so we have to be very careful with making sure that we give the amount of observing time that is earned by a particular proposing team, but that we don't go over that amount by too much. And so in this particular case, these observations that I've set up, which just happen to be a GMOS South observation, this is how long it's supposed to take, and this is how much time is called charged to the PI. So this particular observation is almost entirely science. There's very few on-sky calibrations, and so effectively all the time is charged to me as a principal investigator, and not the extra time to the country. So let's see. Yeah. So okay, this is a complete antithetical situation. So this is GNIRS. This would be an observation like a standard basically. And you can see over here, this is going to take 16 minutes or 17 minutes on sky. But the principal investigator is charged nothing for that time. So this is just saying that we give this 17 minutes of time free to take this calibration. It's charged to the country, but it's not charged to you as a proposer.
And it charged to all 6 countries, or it charged only to the country the PI is at?
So the country that they propose through. So it would be where they're physically located or affiliated, I guess. For every country except for the US. US has the open skies policy. So anybody from anywhere in the world can propose through the US Time Allocation Committee. And they would be, so if they were awarded time, then that would come out of the US's pool of time, even if they were in Uruguay or something like that. Yeah, so this is a super powerful tool. This is basically what we're looking at right now. This is not the exact observation since that information, but this is basically how things are set up for the observation that we're taking now. So this is our peripheral wavefront sensor 2 here. This yellow region here is basically the occultation of the primary wavefront sensor 2 on the science path, kind of. So basically the light comes in, you can think of the light as coming in from the top here. It's occulted, so we wouldn't see any of these sources here because we basically have a mechanical arm that's in the way. And then this is the GNIRS keyhole. And then this little box here is where I think this is probably a IFU observation. So this is where we would receive the light in GNIRS for the science observation. So we do our acquisition with this keyhole here. And then we close up the keyhole and just have a little tiny portion of that for observing whatever target is here. And so this image in the background is the DSS image. It probably only goes to about 19th magnitude in the optical. And so whatever this target is much, much fainter than that. So we can't see anything here. That doesn't mean there's nothing there. It just means it's fainter.
So is the cyan box there what we see as the slit that earlier for the acquisition, or it's different?
Yeah, I think in this case, let me double check. I think in this case, it's an IFU observation. Oh, this was just a random thing, this pinhole. Yeah, basically, so if I switch this over, let's see if I switch this over to, yeah, there we go, okay. So, there, that's basically the slit, right? So that's what we were observing earlier. This is a little bit bigger, so this is 0.45, we're observing 1 arc second, so bigger. You see how the outline of the slit just got bigger. But yeah, that's the basic idea. So we have this giant, well, it's actually fairly small on the sky compared to other near-infrared instruments, but the giant keyhole that we can get context with. And once we're like, okay, cool, there we're at the target, then we close it up. We have just the slit. Let me take that. So we're just going to pause here for a second because we have to decide about the next observation.
Okay, thanks.
What do you think, Denise?
I feel like we probably have time for the very next one.
So for those who join late, I'll just post to the instrument that we are currently using, but I think they'll switch to a different one later in case you guys are interested.
30. You want to try to put it in? I think we can put it in.
It's 5 minutes for the observation.
The actual
so-
observation.
Yeah.
Okay. I'm good with that.
It's scheduled, it's at 5:37, so we're ahead by a bit.
Yeah, but you just move that over to there, right? So That's not the actual
All
schedule.
right, that's true.
okay, that sounds good. One thing I would suggest is take a read of this as we're doing our next thing, because this is open this up. This is our next thing. Yeah, making it easy at the end of the night, Denise. You don't have to do the heavy lifting, actually. It's probably Jenny that's gonna have to do. So yeah, we're just taking our calibrations on GNIRS right now. That's the sound you hear in the background. Every time you hear a beep, that's an observation is completing.
Is this the last exposure just taken, that image you just showed?
Let's see. Yes, that is a flat. It's a lamp on flat, and Denise is now showing us the arc.
Okay, so these are the calibrations.
Exactly, yeah. Yeah. So this is a way of diagnosing the data quality, and you can actually see one of our arc lines here is marked in red. And that's
Jenny, can we slew to the LP 202 one?
that's saturation. That's fine. We have plenty of arc lines that are not saturated. It'll do
Yes.
wavelength calibration.
Maroon X.
Nice to okay. Now that we're basically done with this. So this is our executor. This is what we used to take all of our observations. And so we queue up an observation from that observing tool that I just showed earlier, and then this comes computer. These are observations that we have to take daytime calibrations for. So these are associated with science observations that we took during the night. And so at the end of the night, we'll queue up these and we'll take these observations as we're sleeping. But we just finished the sequence, and so this is showing all the steps that we took for that sequence. So this was the original science observations. You see, there's about 100 to about 3 minutes, all on source. So basically, taking spectra of the science target, and then as soon as we were done with the science target, we took these flat observations and arc observations. But the keen-eyed observer would notice that we didn't take a telluric. So I promised that we took a telluric every time we take a near-infrared spectroscopic observation, but actually we shared the telluric. So we took 2 sets of science observations, one before you guys came on. Then we went to the telluric, and then we took a second set of science observations just for a different target. Telluric can be shared between both because they're close in air mass and close in time. And so that's actually fairly efficient way to schedule these observations, having a shared telluric middle. So I'm going to switch over to our screen that shows our visitor instrument.
So is it currently during
I
acquisition?
think we'll have to do Q+4 as well.
That Q+4.
Sorry, what was that?
I was just wondering what's going on right now. It's acquisition phase for Maroon X targeting?
Exactly, yeah.
Go
So I'm just being quiet. So the night. Okay. It's the crucial moment. Slowly.
Let's do Q+1.
Denise just asked for a movement. That's 1 arc
Right.
second movement at about 30 degrees or so. And what she's doing is grabbing, so that's the science target there, and she's grabbing it and putting it in the fiber. So the Brunex fiber, that's totally fine. It's 10-minute observation.
It's
right?
5.
5, yeah. Okay, so yeah. So Brunex has a tip tilt mirror in it. This is this tip tilt TT here, axis 1, axis 2. And so basically the tip tilt mirror, Denise had the tip tilt mirror move such that the science target, light from the science target, was pegged into the fiber, Brunex fiber. That's this blue circle here. And so we now have counts in the fiber. This is what this peak counts value here. Denise also has a plot up here showing the counts that we're getting every second or so. And so
Right.
this is
Starting science.
monitored throughout the entire observation.
5 minutes.
And so that's a photon counter, and then we have our exposure sequence here. These just put up the other screen. So this is measuring the full width half max, the guider. And it looks like we're about 0.7 arc second. Back this IQ is 70,
85.
85.
I'm gonna show that guiding.
You're not guiding with me too?
Oh, we're not guiding. Oops.
Well, no,
You're just making the tip tilt work a lot harder. It's still staying in there. We are with the tip tilt,
We're not guiding with P2.
right? If you get a nit,
yeah,
Yeah,
Yeah.
well, we can't stop the observation.
yeah, but luckily we have redundancy here, but it's just, we should mark that. Oh gosh.
that's the-
Well, we could always take a second one.
What happened, Jenny?
We lost.
Well, I had to swap.
Oh.
So we had an issue with guiding. Looks like we're gonna have to retake this observation. So you can see the science target went away.
Well, now it's at minus 1500.
So what's our surface, or sorry, what's our sky brightness? Like, can you go to the QT?
We need to take out the cubes.
I mean, we're there. I mean, we're getting, you know, these, honestly, I would just say that there was like a 2-minute loss of time where we weren't exposing, and it's usable. Call it. 'Cause it's gonna get too bright. But it's up to you if you want to try for another 5-minute one.
How long are these?
5 minutes.
Actually lost like 30 seconds or a minute.
Maybe a minute and a half, something like that.
Well, we just hit nautical 12.
Yeah. Yeah, we
That's
just,
okay, I think.
I'll try another.
you can go for another.
I'll just set it to 2 exposure, so I'll take it.
Okay, sounds good. Okay, so what happened? Oh, not exactly sure what happened. Basically, we had a guiding issue. And so these graphs that I'm showing right now are our way of monitoring kind of broad level certain aspects of the telescope and certain aspects of the weather. And so these two graphs here show readings from our primary wavefront sensor 2, which is using partially to guide with X. So we use both this peripheral wavefront sensor and this tip tilt for X internal. And so you can see here this flat line. So basically we're getting no readings from our peripheral wavefront sensor. And this here is our M2 focus value. So as soon as we start getting readings, this starts to change focus changes, and then eventually settles. And
Should
then,
we take out the Q offset? Or it's reading out.
we're at
for-
minus, you're
17,
fine.
okay.
Yeah, as long as it's below 2000 absolute value at the start of the observation. Yeah, so this settles, and then we start getting seeing values. Same thing up here, astigmatism. Just we weren't making any measurements for about 5 minutes or so. So basically, we weren't guiding with our peripheral wavefront sensor, but we were guiding with the next tip tilt. We were just asking a lot more of it because the telescope wasn't guiding, so it was kind of shaking all over the place. So we're reading out right now. And Denise is going to try one more exposure. We're starting to get kind of bright here. But the only other thing we have to do this evening is attempt this focus run. So, and that's the near infrared. So we can do that when it's pretty bright. So here at the bottom of the screen, you can see the readout of the observation. These are different orders here. So all these are either atmospheric bands or something from the stellar photosphere of the target. This is our etalon, which is a white light calibrator, basically. And this gives us a wavelength calibration. So we use two calibrators, one called an etalon, which is this, one called a laser frequency comb, which we turn on at the beginning and the end of each night. And this gives us accurate and precise wavelength solution for our Maroon X observation. And this is why we're able to get down below, I don't know.
Brian, do you have to prepare a
Second.
new one of these, or is it already in here? Copy it.
Yeah, so can you go, okay, right. So no, we've set it up so it's the end of the night one, it's 25. That's all good.
So just use.
Yeah, but just expand it out. Actually, I can go to the screen, so watch. Actually, probably the next. Okay, let's take a look. Yeah, we're fine. Yeah. So you just queued it up, yeah. Okay. Right. So yeah. So we use this laser frequency comb etalon combination. One gives us accuracy, the other gives us precision. We could in principle use the laser frequency comb at all times. Kind of gives us accuracy and precision. But it has a limited lifetime, so we only turn it on for about 20 minutes per day, and then use that calibration from the beginning and end of the night to kind of set the 0 point of the wave.
Sarah, can you say a little bit about this instrument? So I was looking at it. So I assume it is a very high spectral resolution instrument, mainly for exoplanet, like search, or like what is the velocity precision it can reach? And I assume all those laser cubes you said is for improve the wavelength calibration for better velocity precision. Is that correct?
That's exactly correct. Yeah. So this is like extreme radial velocity stuff, which I know nothing about. So I'm actually not, I don't want to misquote in terms of the precision, the radial velocity. So I guess our website says it's below 1 meter per second. So pretty good. I think the Keck Planet Finder, which just got commissioned maybe less than a year ago, probably. That can get to about 10 centimeters per second. but below 1 meter per second, it's fairly rare among instruments. And so the idea is, yeah, so exoplanet finder, I think that's one of the biggest aspects of it. So we have like long-term programs to look for planets around like the closest stars, the sun. And one thing that some PIs do is look for basically molecules in the atmospheres of known exoplanets. And so we do what's called transits. I attempted one earlier this evening. Unfortunately, we didn't get it. The humidity spiked and we didn't get it. But basically, it's where you have the star, you have the planet that occults the star. So we're observing over here. And so you can, basically the star backlights the planetary atmosphere, and by taking an observation of the star plus planet, you can get what absorption features are coming from the planet and not from the stellar photosphere. And then you can do some physics that I know nothing about on the planetary atmospheres. But those are long observations. Those are usually like around 4 hours. And so we just follow the planet as it moves, as it occults the star. Okay, Denise, so we're done exposing.
Okay.
So we can shut everything down on MarinX and we can go to our calibration.
Okay, can we slew to Eng 131?
So we're now done for with science for the night. Science with like principal investigator driven science, and we're going to now try to calibrate our first peripheral wavefront sensor, which is not one that we commonly use, but actually our secondary one, which is in fact our primary one, the one that we use all the time, went down about a week ago, and we didn't have it for several days. And so as a backup, we're going to make sure that our first peripheral wavefront sensor is well calibrated and focused. So if we have enough time before it gets too bright, we're going to do a focus loop. So basically we're going to defocus and then move through focus curve and take images at each focus value and then try to find the optimal focus value.
And I
And
assume
so-
you flew into a bright star for that, which is what it did.
Exactly, yeah. And so Denise, there's some things here that you need to tell Jenny.
Okay.
So all this stuff here, we need to do. We
Right.
can't do it. Just Jenny does it.
Ryan, if you don't mind, can you go to the one of the screen you showed for the TCS status?
Yeah.
One thing.
So we set up guiding, don't introduce astigmatism.
I think I can talk. I just want to let everyone know because I told you guys. So this is the TCS status screen, which is a telescope control system. So this is what this thing here is what the telescope operator controls, and we see as astronomer control the instrument. So you can see where the telescope is pointing at in azimuth elevation. You can also see what is the RA and a DAC. I hope it's somewhere. I actually I don't see it. But this
Actually,
is what.
yeah. So Ting, I have to hide that. Actually, can you move that way?
You interesting. I see you.
I had to hide that because that's proprietary information. But now we're just doing engineering, so I'm happy to open that up.
Yeah, so you can see RA and DAC. So this is where the target is. But I think in the class I mentioned, to me, at least what I think is the most important time is not local time, not like Hawaii time, UTC. It is this LST, you see the local sidereal time. And that is something you always want to know when you decide what to observe next. So that is the RA of the meridian that connects the North Pole and South Pole. And so HA tells you the difference between RA and local sidereal time. So when you want to know at your observation next, your next target, when you observe what is the local sidereal time. So you want to pick a target so you have a small difference between RA and the local sidereal time, or the HA. So this one is very close to Zenith, basically. It has RA almost same as the local sidereal time and depth of 16. So that's why they can
Okay.
point
These are
up on the sky
like
with very
enhanced.
small air mass. The air mass is almost 1, and they are doing these focus.
The disabled corrections and then introduce the 5 microns of zero stigmatism. We get after we do the acquisition. So this is just keyhole stuff. So I mean, as long as we're, basically like we can see it, fine.
Hmm.
Does that make sense?
Yeah.
So all we need to do is see the star.
Okay.
And then we're gonna introduce the stigmatism, and then we're gonna run through the focus. And so we're basically gonna look for minimizing the full width half max and the flip of the PA. And so we have a script that does the measurements for us, which is where is it? Can you scroll down, please? This one.
Okay.
So you can open up a terminal and run them. Yeah, so I don't know if you said this thing, but yeah, we're basically right at transit for this target now, and you can see that the telescope is basically pointed up to zenith, so this is more or less straight up down. And the air mass value here is 1. You can get to figures. And so we chose this target specifically because it's bright and it's up in the sky at transit.
How bright the star is?
I think it's 8th magnitude, something like that. So
And-
originally I did use a 5th magnitude star for this.
Guiding.
Turn off the M1 correction. Okay.
So
Well, yeah, you need to introduce 5 microns of zero as
hold up. We should first do the acquisition. So take the first image. Yeah, pause. Yeah, we should. Genius. So
Brian, I know you are probably busy. I think it's cool to show this acquisition, this focus thing when it's available. One more thing it would be good if you could show is, to me, like astronomers also wanted to know how the weather is in real time. So like the TCS you just showed has C in there, and it seems the C is great. It's 0.4 arcsecond right now. But
Yeah.
can you also maybe show another screen where you guys monitor the weather condition regularly and know whether you need to close the dome if the humidity or the dust or the wind is too high? Maybe it would be good to show some of those if it's possible to get some idea for the students.
yeah, I'd be happy to. Yeah, so actually, let's see where so hi on this screen here. So these televisions here are our Gemini cloud cams, and it gives us an idea of what they're hypersensitive cameras, and it gives us an idea of what the sky conditions are. We're actually down at about 300 feet above sea level there. Sorry, you guys are Canadian, so 100 meters above sea level. And so we're not on the summit of Maunakea, so we can't see it through our eyes. We have all our weather server up here. You guys can't see it, but there's numbers up there, and that tells us humidity and wind direction, all this kind of stuff. The tools that I showed you earlier that had all the different colored bars, that gives us an idea of the weather. So we have all sorts of monitors for that. And then
What do we do?
so are you so it's imaging? Yeah. Okay, so go to the bottom and press X.
The bottom page.
Hilo. Yep. Good, so the offsets, and then
Okay, sending off.
and it's sticking to.
Uh,
So just ask Jenny.
So I need to add 5 microns of zero astigmatism. Why does it say O and zero?
Offsets are in.
And then we're gonna want to go to also do our first focus offset.
5. The astig.
Yeah. And then go to what?
So we're gonna go to our first focus value here. So that would be minus 0.16. So Jenny needs that
In where?
in the focus offset.
Okay, can we go to minus 0.16 in focus offset?
Have the original value.
No.
I think it's something like minus 0.04. It should be somewhere.
And you want minus point, what?
16.
That was completely, that's from memory. Plus.
I think you're. Very placed.
So Denise, I would put pause after the 3. So we want basically 3 exposures at each focus value. Okay. And so we want to wait for things to settle. That's really important. And then we can go ahead with the first 3. And then we just move to the next focus value, wait for things to settle, next 3, so on
What
and so forth.
is 20?
Yeah, you can always add. I don't know how many we need. Let's see. We need 27. 20. So you can, Denise, you can that to 27.
You mean 28? The first one was
Sorry.
the first one was the acquisition.
20, no, 27, 9 times 3.
Yeah,
Oh,
plus
but the first one
one.
was acquisition, yeah. So sync that and yeah, sync that. Are you guiding?
Yeah.
Ah, got it. Okay, so it's not even gonna register P2 counts.
No, the last time we did this, we didn't get any of those values and one himself.
So do we just go?
So that looks reasonably. M2 looks like it's still moving a bit. But I think you're okay to go.
What do I do for the starting the data times
What do you mean?
in the night log?
Just say Eng 131.
When do we start taking data?
When we did the acquisition, basically. But let's stick with this because Denise, we're like on a really tight time schedule here. So okay, Jenny, can you go? No, are you losing it? Or is we're just passing zenith or what?
We are at Zenith. We are 5 minutes past it. Transit.
When you can, Jenny, can you move to minus 0.12 for the focus value?
Sure.
And Denise, you can start the GNIRS focus loop on for ideal. So scroll down. Okay, thank you, Jenny.
Do I have to put in UT day?
Actually, I think this has changed. So here, actually. Yeah, I don't think that's right. The 29th.
Yes.
I think we have to do first last. So we are using P1.
One.
So those are first values. So we had our original. Oh, we even have our original focus value. That's great.
Should we run the next set?
When this set is settled. Yeah, we're good to go. Go ahead. So Jenny, it was minus 0.049. Is that what I said?
Yeah.
Okay. Wow. Can't believe I remember that. And what's our next focus value going to be? 8.
Yeah, it was 864.
Minus 0.08.
Yeah.
Yeah. Okay. So Jenny, can you go to minus 0.08, please? So let's wait for this to settle.
I'm regretting it.
Do we not run each set as it comes in, or
What's that?
do we not just run each one?
Yeah, you can do that. Yeah, yeah. So you can close out of those.
Wait,
Just do it again. It's fine. It should automatically find everything today. On again. There you go. Okay, now we're starting to get something. Oh wow. Okay, this is gonna be interesting. Okay. Yeah, I think you're probably okay to go. Ting, I see in the chat that you have to leave fairly soon. So we're happy to stay if your students would like to stay, or we're happy to call the session as people would like.
Yeah, I don't know
I
if
don't
any
know.
particular.
railing.
Table, right?
Should I pause here or leave it? Oh,
Are you still guiding, Jenny, or no?
I have to take another sky, right?
Yeah, we're basically running into the sun now. So yeah, there's not too much observing left.
So were you able to finish this focus sequence before the twilight?
Okay, we're guiding.
Yeah, okay, see.
Just run it?
No, we have we're probably about a third of the way through right now. If we get lucky, we will get at least a few more observations, and maybe we can get something that
we're on minus 06, right?
we're minus 08, I think.
Oh,
But hold on. So maybe we want to move a little bit more. So we have the minus 0.4. So maybe why don't we try plus 0.04, and then we'll try plus 0.12 just to give us a nice dynamic range. So Jenny, can you go plus 0.04, please? Denise, can you rerun the plot? Or new observations?
takes so long to run.
Yeah, I don't know. It's having it's looking at data flow and it's taking a long time.
Can I reconfigure GNIRS files?
It's the same. Yeah. Yeah, so basically it's giving, it's kind of flat actually. So we're looking at the full width half max. Oh, sorry, I'm showing. So full width half max is a function of focus value.
And we're guiding.
And so actually our full width half max is kind of flat. As a function of focus, which is good in one sense.
So the curve is expected and the dots are what you observed?
Dots are what we observed. The curve is the fit, like weird fit. It's basically simultaneously fitting the peak, the flux as a function of focus value, the eccentricity, the angle of the star, and the full width half max.
I'm guiding.
And maybe my last question, so I know this is a special run you usually don't do every night, but is there any particular thing you do at the end of the night after the science exposures?
Yeah, great question. So we try to use every possible
We're guiding again.
open shutter time that we can. So we would normally probably be taking twilight flats right now. So we would be taking GMOS twilight flats. We have a certain number that we need for making sure that we get a good basically median stacking. And so we usually want about 25 per setup. And so any observations that were
I'm guiding. I need to take skies.
yeah, we can get 4 more observations, that would be awesome. Yeah, that's right. So yeah, we have tons of programs, and those programs have imaging in different bands, and so we try to get as much as we possibly can every night. So I think we need 25 flats to be able to get a reasonable median.
Sunrise is in 10 minutes.
And yeah, we try to do that for every season. So let's go to plus. You got plus 0.12, and that'll be our last one.
Yeah, I have to go, but I'm not sure if any people in the audience has questions, maybe before we call the session. Okay, if not, I hope it's useful for our students, and I want to thank Brian and Jamika and all of the Gemini folks to organizing and let us to do this Shadow the Scientist program. It's nice to see 2 Gemini instruments and how you guys do the observations.
Yeah, thank you so much for setting this up, and happy to share the end of our night with you.